Okay, so there was one day, probably when I did distance, I should have just given you this definition because it has to do with the eccentricity, but I think I just quickly mentioned it when it came up in a later lecture. But if you ever see the word central vertex, this is just a vertex where the eccentricity of that vertex is equal to the radius of the graph. Right. So if you want, you could put G here, where G is your graph, radius within the graph. So for example, just since it probably would be good practice anyway, why don't I give you a graph and let's see if we can calculate the eccentricities for each of these vertices. So in red, let's write out the eccentricity, right? So remember that the distance between a vertex and every other vertex is the minimum path length, right? So the distance from this vertex to this one is 1, even though that there is a path length that's longer than that, right? 3, okay? So the distance is minimum. So you calculate all those distances and the eccentricity will be the maximum among all those distances. So distance 1, 1, 2, 3, 4. So it looks like this should be 4, right? And by parallel, if this is 4, then this one's going to be 4 as well, right? Just from the symmetry of the situation. That's not always going to be the case. You have to be a little bit careful. But if you just stare at this vertex, that one is definitely the furthest away, right? Okay. These ones are, this is 3 and 3 to get to this one. And this one is distance, max distance 2, right? So 1, 1, 1. And then these two are distance 2 away. And then this one is distance 3 away from this vertex. Okay, so what's the radius of this graph? The radius would be the minimum eccentricity, which is 2. And the diameter is 4, right? The maximum eccentricity. And now this vertex right here is a central vertex. Okay, because it is a vertex where the eccentricity is actually equal to the radius. Now your graph may have many central vertices, but just by definition, it's just a vertex where the eccentricity is equal to the radius. Okay, and then what you could actually do is you can induce a subgraph called the center of the graph. So the center of a graph is a subgraph induced by the vertices with the minimum eccentricity. Okay, meaning induced by vertices where the eccentricity is equal to that radius, right? So let me give you an example where you might not end up with like a trivial vertex. Like here, this would just be a vertex, right? Okay, let me give you an example where you don't just end up with a vertex. Okay. So if we draw this graph, eccentricities, this vertex is distance 4 from over here, right? But 1 and 2 and 3. So max distance there is 4. This one will also be 4 going this way, right? 1, 2, 3, and 4. These are distance 3s, and then these are 2s. So you see that I actually have many central vertices in this graph, right? There's 4 of them. So there are several central vertices here. So if I draw those vertices out, so I have 4 of them, right? So this is G, okay? And if I draw these 4 vertices out, what is the subgraph that's induced by these vertices? Do you remember the definition is you tell me where the vertices are, and then I'm gonna throw in any edge that happens to be adjacent that's built from those vertices, right? So they induce the other connection. So for example, do you see, if I have these 2 vertices in the original graph, they are adjacent to each other. So that's going to induce this connection here, and same thing down here. So this would actually be the center. Is everyone okay with that? So remember, the induced subgraph is you throw in all the edges that you can possibly make with the vertices that are here. You're not going to add anything extra. You're only going to throw in the ones that are present up here that use those vertices. Is that okay? Like I'm not going to have these half edges hanging off or something like that, or more connections there, because It has to be a subgraph. Okay. So this would be, this whole thing right here would be the center of G. Okay. And you could use notation for that. If I label those vertices, do you remember we had notation for an induced subgraph on a vertex set? You could just label the vertex set as that you want to induce by as at X. X would be this collection of these 4 vertices, and then you would have this notation G bracket X. So, or you could use a colon, but that's not really that important. Is that okay? Any questions with that? Yeah.
Yeah, so in this case, we don't actually have single vertex as the center. How do you know it?
Well, how do you know? You would actually have to calculate all the eccentricities, right?
I mean, I know. I was asking, how do you denote it? I mean, how do you write it down? How do you explain it?
Oh, well, I would just say that these are central vertices, okay, just like I did here.
Like you list all of them?
Well, it depends on what they're asking. Like if the thing here is not labeled, right? I don't have names for the vertices, but if you did, you could say the central vertices are, you know, X1, X2, X3, X4, and you could label them if you want. So that's one thing you could do. But here I'm just kind of giving you the example with the pictures, and then I'm labeling in red the eccentricities. So if you were going to do that, it might be good to tell me what the red means. Maybe say in red, that's the eccentricities. And then if you want to tell me what they are, you could label them like X1, X2, X3, X4, and then you could say central vertices X1, X2, X3, X4. So if you wanted to do something like that, that would not be a bad idea. Or you could just draw an arrow to them or something like that. You know, depends on what you have to do in the problem. Okay. And if you did this, then if you let X be this collection, the center would actually be equal to G being induced by that. That's notation that we had in the past. Okay, so here's kind of an interesting property. I thought maybe you could prove this because it actually doesn't take too long to prove this, but there is a relationship between the radius and the diameter. And as soon as you're thinking of a circle where those names are more commonly used, right, you know that the diameter is twice the radius, right? So maybe there's a connection there, and there actually is, right? So one thing that you can definitely prove is in a connected graph G, the radius is always less than or equal to the diameter, and the diameter is always less than or equal to twice the radius. So it's close to that result, right? But it's similar to that relationship. Now, one of these inequalities is very easy to prove because the definition. So this one is clear by the definition of radius and diameter. Why is that? Well, the radius is the minimum eccentricity, and this one's the maximum eccentricity. So surely the minimum eccentricity needs to be less than or equal to the maximum. They could be equal, so that's why you have to have less than or equal to there, right? If you had, for example, what's something where the radius and diameter would be equal? You think of a graph where the eccentricity, well, if that happened, all the eccentricities would have to be the same, right? Because the minimum would have to be equal to the maximum. And that would happen, might, if everything was distance 2, is that could happen. That's one example that could happen. Like a 3 cycle. Yeah, more generally a clique or a complete graph, right? In a complete graph, everything is adjacent. So what's the distance between any 2 vertices is 1. So then the eccentricity and radius would be equal, right? So that's sort of the more connections that you have, the closer these two should be, right? And the more sparse the graph is, the more spread out things will be, then this gap will be bigger. So you see these 2 global parameters kind of give you some global structural information, but it's not going to be perfect. Yeah. How do you prove the other one? Well, the other one, let's prove this. So proof of the diameter being less than or equal to 2 times the radius the trick here is we're just going to use the triangle inequality from before. So pick U and V in V such that the distance between U and V is actually equal to the diameter of the graph. Now, by definition, the diameter of that graph, you can think of it two different ways, right? The diameter is the maximum distance in the entire graph, or you can think of it as the maximum eccentricity. So do we all agree that such a pair has to exist in the first place? Because if it didn't, then there would have to be something smaller, and then that would be the diameter, right? So there has to be some distance in the graph that's maximum. So there is a pair that exists where this is true, okay? There may be many pairs, but you're just going to pick a pair where that's true. Now, what can we say? Now, also pick a central vertex. Let's call it W in your vertex set. And we definitely have to have a central vertex because how is a central vertex defined? That's one where the eccentricity is the minimum. And that minimum is from a finite set. So there has to exist something that has minimum eccentricity, okay? And now here's where the magic works, which is the distance between U and V, which is the diameter, right? So the diameter is equal to this. You agree that this has to be less than or equal to the distance from U to W plus the distance from W to V. So this is one of the original properties of the distance function. If you go back to your distance function, you have this triangle inequality here. That if you pick any three vertices, the distance between U and, well, in our case, it's going to go U and V, would have to be less than or equal to the sum of the distances from like U to W and then over here. So, okay with that? So this is by triangle inequality, okay? And now what can we do? Well, W is a central vertex, right? So what is the eccentricity of W? Actually, it's equal to the radius, right? But this thing, this U, might actually be closer to it, right? So everyone caught up so far? All right, let's come up here for a second. So this central vertex is 2, right? Now, so for that to happen, there are some vertices out here that happen to have distance 2 from it, right? But if my U and my V are a little bit closer, do you agree that the distance between this central vertex and some of the other ones might actually be less than the radius? Is that possible? Or it could be equal. It could be equal or less, but it could never be greater, right? Could you have that this central vertex is distance bigger than the radius from any other vertex? Is that possible? If that was possible, then it wouldn't be the central vertex, right? Because by definition, the eccentricity, which is the maximum distance, is equal to the radius, right? So you can't have, if you're at the center, you cannot have a vertex further than the radius, right? From that one. If you're sitting at something else, like something that would give you the diameter, then surely that can happen, right? But if you're at the center, you know that the farthest something is away from you is the radius, right? So in other words, coming back down here, I don't know how far apart these two are, but I definitely know that this one is less than or equal to the radius because W is a central vertex. And I also know this one is less than or equal to the radius because W is a central vertex. Okay. And what does that tell you? Yeah. This is 2 times the radius, right? So that's it. Okay. I thought that would be a fun problem to work on together. That's not terrible. And it uses some of the previous properties. Any questions with that? Again, remember, here to here is because since W is W is central. W is central. Okay, so there can't be anything further away than the radius. So this is definitely bounded above by the radius. It could be equal. Like if they were, let's say your U and your V were these two vertices, they are equal to the diameter, right? And then the central vertex is actually equal to, it'd be 2 plus 2 there. You see in this one? Well, I mean, here they are actually, it is twice, right? It's actually equal to, right? But what I'm saying is in the theorem, it could be that your diameter, it just has to be less than twice this, okay? But in this one, it's actually equal. So, good. All right, let's go through some of the homework problems, or maybe we could go over definitions as well. Would you like me to go over a couple of the homework problems that maybe some people did not get? So, oh, okay. So one thing that we worked on together, do you guys remember that for number 3 here, prove that if G is self-complementary, then the order of n, or either n or n minus 1 must be divisible by 4. Now we did all this work together to get to the point where the number of edges would be n times n minus 1 over 4, right? We did all this together. Are we okay with that? So looking back at the notes, we got up to here. The only thing I was looking for at this point was, how do you argue that one of these has to be divisible by 4? You can't just say that they are, because it's possible that one is divisible by 2 and the other is divisible by 2. So you just have to argue to me why one of them is forced to be divisible by 4. So you could either say they're consecutive integers, so one of them is even and one of them is odd. The odd one can't possibly be divisible by 4 or 2, right? So it forces the other one to be divisible by 4. Another way to finish that one is you could say they're relatively prime with each other, so they can't share any factors other than 1, right? Which would mean, I mean, this thing only has factors of 2 in it, so that's another way to do it. Okay? But somehow you have to give me an argument for why this is. Now, if that was a prime, you could just reference Euclid's lemma, but it's not a prime. So you have to give me a little bit of something there. Number 5, most of you did pretty well with this, use the Havel-Hakimi theorem. Just something to keep in mind, you don't always have to use the entire robust theory to check if it's not graphical, because we have a couple of results that you could use to verify that it's not graphical. For example, what are some things that some of you did use? I know one of you checked the sum of the degrees, right? If you took the sum of all the degrees and it was ever an odd number, isn't that impossible? Because of the handshaking lemma, right? Handshaking lemma says the sum of the degrees should always be twice the number of edges. So if you take the sum and you get an odd number, it can't possibly be graphical, right? Another thing some of you did was you looked at how many odd degree vertices you have, and there was a result that says the number of odd degree vertices should always be even. So if you had an odd number of odd vertices, that's also impossible, right? So it's not always going to help you, right? So for example, how did this go? So this one was, the first one's not graphical, right? Not graphical. And then was it graphical, graphical, not graphical? Is that what it was? Now you can get all of this from Havel-Hakimi, doing every single one of those. And most of you did that. I'm just pointing out, for example, this last one, look at this. So this last one is not graphical. Do you see that there's a degrees 5, 5, and 3 there? So without even doing Hawa-Hakimi, this guy is definitely not graphical because there's an odd number of odd vertices. See that? Also, if you take the sum, is that like 31?
Yes.
So that's another way, right? If you take the sum of those, you get an odd number. That's not graphical. I'm just giving you some tips to shorten some of it, you know. Or if you do have a Hakimi and then you notice one of those, then it would say that the resulting thing is not graphical and therefore the original is not graphical because it's an if and only if. So that's a very clever thing to keep in mind. One of these, I believe you do have a Hakimi once or twice, like this one. And then you get the graphical, what would you get? You'd get 3, 2, 1, 0, 0. So after doing Hawa-Hakimi once, you would get this, right? You'd circle the first one, subtract 1 from the next 4. So you'd get 3, 2, 1, 0, 0. We okay with this? Of course, you would be a lot neater than I'm doing right here, which all of you were. I'm just trying to make this faster. Once you get to this point, do you guys see that it's not graphical? Most of you said that it was not graphical because if you just consider the first 4 vertices here, if you can't have a list of distinct vertices, degrees like that, because this would force you to have a degree 3 vertex and a degree 0 vertex among 4 vertices, which is not possible in a simple graph at least, right? So everything, any problem that I give you, you're always going to assume that it's simple unless I somehow say that it's not simple. Okay, so don't draw any like multi edges or loops or anything like that. Because Hawa-Hakimi, I mean, if you can draw multi edges and loops, it'll screw up everything. Is this okay? This is kind of like the ludicrous graph situation. You'd have 4 vertices and you'd have distinct degrees for each one, which is impossible. But just the argument for this is you can't have like among these 4 vertices, you can't have one of degree 3, which would then be connected to all of the successive ones, and a degree 0. So the quick argument is you can't have one of maximum and degree possible, which is n minus 1 among n vertices, and 0. That's impossible, right? I mean, ignoring the ludicrous graph thing, you can't have this happen. You guys agree? Among 4 vertices, I cannot have a vertex of degree 3 because it would be connected to all of the other ones, and then also have a random degree 0 vertex out there because it has to be connected to something, right? Like if you just draw, there's 5 vertices, but among these 4, as soon as I say that I have a degree 3, there is no way to have a degree 0 vertex. You see that? It's impossible to have a degree 0 and a degree n minus 1 vertex among n vertices. It's not possible. Is that helpful? I think most of you argued something like that.
So what you're saying is usually 0 and n minus 1 don't go together, right?
Yes, yeah. Among n of them. If you happen to have a bunch of extra zeros, you can ignore those and do the same argument for the fewer vertices that you have. I think in the list of, didn't we write out a list of properties for the degree sequence? I think that might have been one of them that was in there. The day that we did Hawa-Hakimi. Maybe not, I don't know. That also in the distance notes, number 6. I'm trying to remember which note set the Hawa-Hakimi is in. No. 4? 3, thanks. Yeah, so here we go. So before, this is a note set number 3, before we stated Hawa-Hakimi, there are some observations here, right? Every vertex degree has to be between 0 and n-1 among n vertices, right? And you cannot have the maximum degree be n-1 and have an isolated vertex. You cannot have a 0 and an n-1 coexist as degrees. So that's what we were saying there. So be aware that even though you could have a sequence that's longer than that, see there's 5 vertices here. This is like n-2. If you ignore one of those zeros, now you have 4 vertices, and then you'd have an n-1 and a 0. So you can generalize this result by kind of ignoring some of those zeros, okay? Or you can generalize it to say that you can't have one of n minus how many zeros that you would have in the sequence, right? Something like that.
It's kind of like you're taking the induced sum.
Yeah. So these are some other things to check, right? The sum of all the degrees is evenly many odd vertices. And so these are some necessary conditions, right? The sum should be even. You can't have 0 and n-1 coexist. And if you happen to have a degree that's like too big for your list, that's another thing you could check real quick, right? But a lot of these will come up as you're doing Hawa-Hakimi, right? It'll just get screwed up. We okay with that? And keep in mind that everything's simple. So it's good that we caught all this on the homework, right? So when you do the exam, then everything will be good, right? Any question with Hawa-Hakimi? Okay, so looking back at this homework. Yeah. So, oh, the girth of these, yeah. So as soon as you're bigger than 3, if you're less than this was infinity if your n is 1 or 2, but then 3 if you're bigger than or equal to 3, right? Because then you have you definitely have a 3 cycle. Here, this is as soon as you have 2 vertices in each partition, then the girth will be 4, right? And then this one was also 4, right? Well, if k is 2, what does that look like? Yeah. Well, we have the cubic graph right here. So here's Q2. Q1, it has no cycles, so that would technically have infinite girth. But for this one, I'm having you consider k is greater than or equal to 2 anyway. But as soon as you're here, there's always going to be a square inside this. You will not create a triangle. So the girth will be a 4 for anything bigger than this. I think almost everyone kind of said that. I mean, it's built inductively, right? So you could argue there's definitely a 4, and then you could just try to argue why you would never have a triangle. In order to have a triangle, you'd have to have 3 vertices that differ by, they'd be distance 1 from each other, in the sense that this is the one we're talking about, right? Yeah.
Because it's inductively built.
Yeah. I mean, if you wanted to have a triangle, you'd have to have 3 binary sequences that are all distance 1 away from each other. And you have to pick one coordinate to flip, right? Then you pick another coordinate to flip. Because if you flip that same one, you'd be back here. If you pick that other coordinate to flip. Now that you picked another coordinate, it's impossible for the original one to be 1 step away, because you have to flip 2 coordinates. So that's kind of, I think that's how you could kind of argue that you couldn't have a triangle in this structure here, because you'd have to have at least 2 coordinates flip which would then create a square, not a triangle, or minimally it would create that. You have cycles that are longer than 4, right? Like a 6 cycle here, that's fine. But I think to get back, it's kind of like there's a parity condition there. The number of flips would have to be even, I think.
I forgot, but how did you assign the 1, 0, 0, 1?
Yeah, it's right here. It says, I mean, all you're doing is you're taking k tuples. They're binary vectors, right? And the inductive procedure is, how many binary vectors are there of length 1? Well, there's 0 and 1. How many of length 2? Well, there'd be 4. 2. It's 2 to the n. That's how many vertices there are. But the inductive procedure is you just take the previous one and you tack on either zeros or ones, right? So if I tack on zeros to the beginning of this, I guess, and I tack on ones to the beginning of this, it'll preserve this connection here and here. But now by tacking on the zeros and the ones like I did, so these will be connected, but now they're going to definitely be different in that first position. So that's why they'll be connected here and here. Okay. But I'm not going to have 0, 0 and 1, 1 connected because they differ in 2 positions. You see? You only draw a connection if they differ in exactly 1 position. So then to get the next step, just draw the exact, you draw that thing twice. Every time you just draw it twice. So draw that, you have 2 layers here. You see the front and the back. And then you're going to tack on a 0 and you'll preserve this. If I put on a 0, then that third coordinate doesn't matter to the connectivity, right? There's no differences created. So I'm just going to have that same structure. If I tack on a 1 in that third position, I'm going to have that same structure because I'm not introducing more differences. But now I'll have 2 layers of all zeros and all ones. And now the only difference between the 0, 0, 0 and the 0, 0, 1 within these layers is that third position. So the layers will connect to each other precisely in the right positions. And then you keep going. So then you get the hypercube situation. It would look like this. You just draw the cube twice, right? And so on. And then you get higher dimensional hypercubes and all that stuff. Oh, another thing you could argue is you could just argue that it's not bipartite. So therefore it couldn't be, you couldn't have a 3 cycle. That'd be another way you could argue it. So you'd have to figure out how to argue that it's bipartite. But I think you could do that a couple different ways. Later on when we learn about coloring, it might be faster because you could think about the differences allow you to color adjacent vertices. And it kind of would give us back to this 2 flipping thing. Yeah. So Koenig's theorem could also be useful here. 7. So one thing for 7, I just wanted to be sure everyone saw this. So in KMN, right? So you have M vertices over here, and you have N vertices over here. Okay. The question is, how many edges are in this graph? There's 2 ways that you could do this problem. One way is you could just look at the left here and you could say, well, I'm going to have edges. It's a complete bipartite, right? So I'm going to draw in all the possible edges I have here. So in other words, how many edges is that vertex going to, what's the degree of that vertex? The degree is going to be, so if this one is size M, and this one is size N, the degree of V1 is N, right? There's N vertices over here, so this thing is going to be connected to N of those, right? And then the same thing with the next one and the next one and so on, right? So what would the total number, here's 2 ways that you could do this. So solution 1, total number of edges. All the edges connect this side to this side, right? So actually I can count all the edges by just looking at this partition set. I don't actually have to look over here at all. You see that? All I have to do is just count up the edges. Well, I know there's N edges coming out of here, N edges coming out of the next one, and so on and so forth. So isn't the total number N plus N plus N plus n, a total of m times, which would be m times n. You okay with that? Another way that you could do it is you could actually take the sum of all the degrees in the entire graph. Now, what are the degrees over here? The degrees over here would be whatever you want to label that thing. Let's call it u. This would be m, right? So all of these degrees would be m because they're connected to m things over here. So what's the solution to? What's the sum of all the degrees in the graph? Well, you're going to have n plus n, blah, 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 plus n, plus m plus m plus da, 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 plus m, right? Because I have all these degrees over here, which are all n's, and I have all these degrees, which are m's, and I have m of these, and I have n of these. So do you see that it would actually be nm plus nm, which is 2nm, right? But handshaking lemma says that the sum of the degrees is 2 times the number of edges, right? So by handshaking lemma, 2 times the number of edges, handshake would tell you, well, you divide both sides by 2, and the number of edges will be this. We okay with that? See that? So number of edges would be 2nm divided by 2, which would be nm. So you could do it that way too. Any questions with that? Since it was bipartite, I probably would just choose to do it the first way, because the only reason you could do solution 1 is because it's bipartite. You're guaranteed all the edges. I don't even have to look at the second partition set, right? I know all the edges are here. They come out of, they're connected to all the things over here. So I don't even have to look at the second one. This would be a good approach if you were looking at a general graph, okay? So don't dismiss solution 2. It looks like it's more work. If you were in an arbitrary graph, this is actually a good solution, because if you know all the degrees, that's how you would calculate the thing, okay? 7b is pretty much just doing 3 of these. If you were looking at K, M, N, P, right? Now you have 3 partitions, right? This first one is size M, the second one is size N, the third one is size P, and then you could just do the same trick, and you could just think of these things as, you could just do the same kind of idea. So look at this. So this vertex, you're going to have N things coming out to be connected to these guys, and P things coming out to be connected to this one over here, right? So you could actually do this a bunch of different ways. One way is you could just think of it as, oh, let's count the number of edges going between these two. That's like a bipartite graph, which you just did, right, from part A there. So number of edges between V1 and V2 is what? Between these two is going to be M times N, right? Here, let me just show you a small one real quick. So you see between these two, I'm going to have, it's bipartite between these two, bipartite between these two, and bipartite between these two. So do you see, I could just use the A calculation 3 times. You see that? So number of edges between V1 and V3. So between these two, I'm going to have M times P. And then V, so between V2 and V3, it'll be NP. So then the total will be the sum of these. See that? The alternative is just do the same thing with the degrees. You could take the sum of all the degrees and then divide it by 2. We're okay with that? Like up here, what's the degree? The degree of that vertex would be n plus p. You see that? So if you started to take the sum of all the degrees, it would be more work, but you could get it that way. I think it's faster to just use A because you can just think of it as 3 bipartite graphs, all connected.
It's a counting problem.
Yeah. Yeah. Does that help? So I think a lot of you had the intuition there, but you didn't know how to do the count. That's all. Just making sure it was pretty clear. I think other than that, most of you, those were the only things on the homework that I kind of noticed. You guys did pretty well on that. And the next homework, I think you did even better on. Just make sure if you're going to cite Koenig's theorem, I mean, that one's big enough that you should probably say the name of it or something like that on the exam, okay? Bipartite graphs can't, they can't have odd cycles, or using the other way, say there are no odd cycles, therefore it's bipartite. It's an if and only if classification. Oh, you know which one? Some of you, so I mentioned this in class. Is it okay? So the only one that I think a few people missed, I spent a little bit of time explaining this. So number 4 here said determine the minimum positive integer m such that every graph of order n and size m is connected. Now that's different than saying what is the minimum number of edges required to have a connected graph. Do you see that? That's different. This is saying what's the minimum number of edges I have to tell you I have in order to be guaranteed I'm connected. So some of you accidentally said, well, you only need n minus 1, which is not the case, right? So some of you said m is n minus 1. Well, what if I had 4 vertices? So here n is 4. What is n minus 1? 3, right? Can I create a graph with 3 edges and 4 vertices that is not connected? Yeah, I could just make this triangle, right? Do you see now I have 3 edges, 4 vertices, but it's not connected. My question is, how many edges do I have to have in order to be guaranteed there's no way that I could draw a disconnected graph, right? So you're trying to figure out, it's actually more than this, right? Okay. And the trick that I was mentioning to think about is if you have n vertices, so n vertices, using the same trick, what's the maximum number of edges that I could put in? So ignore this isolated vertex. Okay. What's the max number of edges we can add and have a disconnected graph? Isn't this how you could do it? What you could do is you could just say, let's not connect anything to this red isolated vertex, but let's maximize the number of connections here. That would be a complete graph, right? You see that you would end up with a complete graph on n minus 1 vertices. And then you'd have that isolated vertex, right? So maximum number of edges that you can have and still be disconnected, you'd have this kn minus 1. So then now what do I do? At this point, as soon as, if I require that I have one more edge, you see I can't connect anything else that's up here because I've already maximized the number of connections. So I would absolutely be forced to connect that isolated vertex to one of these other vertices. See that? So now if, so the the number of edges in this is what? N minus 1 choose 2. Okay. Now, if we add one more edge, the entire graph will be connected, right? So if I take my n minus 1 choose 2 and I just add 1 to it, right? Now that isolated vertex will no longer be isolated, and it'll have to be connected to one of those. I don't know which one, but now there'll be no way to actually draw a disconnected graph. Because you essentially maximize the number of connections away from one vertex. And now, well, I have one more than that. There's no choice now. I have to be connected because it's a simple graph, right? I'm not going to draw multi-edges. This would be a really boring question if you allowed that, right? Because I could just have an infinite number of multi-edges between two vertices. Okay, do you guys see the difference now between those two? It's still important to remember the other extreme. The other extreme is, this is the minimum number of edges that I could have and be connected, right? So for example, could you prove if M is strictly less than that, it's disconnected? That would be another good problem. If M is less than that, it would have to be disconnected, right? Not this extreme. This one is saying as soon as I have this many, I know I'm connected. Anything more than this, you're still connected, right? Anything less than this, you could be disconnected. So isn't this interesting? It's sort of like the Goldilocks theorem. You see this? So number of edges. So think about this, number of edges. Okay. Here, so M is n minus 1. And here is M is equal to n minus 1, choose 2 plus 1. You see, if anything is bigger than this or equal, you're guaranteed connected, right? Aren't you? If you are less than this, you're guaranteed disconnected, aren't you? You see that? Now, if you're equal, you could be connected still, okay? So less than this. You are guaranteed disconnected. And then this is your maybe connected. You might not know, right? Could be connected, might not be connected. You could produce examples of connected for sure. Down here, your trees, right? Isn't this a tree? Minimally connected as a tree. So isn't that kind of interesting to think about?
I guess you could feel like.
Oh yes, that's actually that's a very important question. In general, among all graphs, what's the likelihood that the graph is connected? It was a huge unsolved problem for a long time, and it created a whole probability theory of graph theory. Yeah.
Yeah, because when I think about this stuff, guaranteed is obviously 100%.
Yeah.
But then maybe it's when you get the probability.
Yeah, so in probability, you have like you have likelihood or the expectation or yeah, all this kind of stuff. Yeah, this was very important. You build your yeah, there's a whole area of math of graph theory just devoted to probabilistic graph theory. And it's very useful because if you're trying to figure out, like, take any parameter that you could study, what is the likelihood that it has that property? If most graphs have that property, then that's actually really interesting. If few graphs have that property, it's also interesting. If no graphs or every graph have that property, then it's a dumb property, right? You could write a whole thesis on some amazing theorem, but then if no graphs have that property, then then it's useless, right? And if everything has that property, then it's also kind of useless because it doesn't distinguish graphs, okay? But if you come up with a property where some things have it, but not everything has it, and it's still interesting, you know?
Every graph with a vertex, every graph has a vertex.
Yeah. Well, see, this right here shows you why connection is kind of an interesting property. Well, this is one reason. I've never thought of it like this before, but that's kind of an interesting thing, right? So you kind of have the two extremes. All right. Well, I think we are out of. Wait, are we out of time? Yeah, we're out of time. But I'm happy to answer any more questions you guys have because I have office hours now anyway. Okay. Any last minute things? What are you guys most worried about with the exam? I would say go through all those notes, maybe make an index card for each definition. When I usually, okay, in the past, when I gave this class an exam, there was usually at the beginning just definitions because the definitions in graph theory are the most important thing. And I'm trying to get you to, I don't know, memorize some of these definitions because they're so important. But if you're going to have your notes, it kind of defeats that point. But I still suggest you make those index cards because as you're working through some of these theorems, it's going to be nice to have a lot of recall memory on some of these important things, theorems and whatnot. Some of these problems are definitely more challenging than other ones, right? So it's really hard to look at this homework, for example, and say how long it's going to take because some of those problems are definitely harder than other ones. Some of them were very short, right?
Yeah, this isn't like a calculation class.
Yeah. Well, there's also limits to these, right? The smallest number is 0, right? And the biggest is the n choose 2, right? I've never thought of it like that, but that's kind of interesting. Yeah. Maybe you could think about other parameters having something similar to that we've seen. All right, I will send it out on Thursday evening, and you guys you'll do it on Friday. Okay, I'll send you more information as well. All right, have a good one.
Yeah, this is your probably go on any connected graph, the probability that it's connected is like.
Yeah. Well, how they do it, so you do this, you say, what is okay, so you create an object called a random graph. What you do is you have n vertices, and you have a probability between arbitrary vertices, when will you have an edge, okay? So you have to first have that structure. If you say probability 1, then it's going to be a complete graph, right? If you say probability is like a half, see, that's kind of interesting. It's like half the time you will have an edge, half the time you will not have an edge. Then what you do is, depending on that probability threshold you just gave, then you can ask the question, what is the probability that that graph will be connected or not? So if you gave a probability that half the time the edge will be there, half it will not, what's the probability that that graph is connected?
That's probably going to be dependent on the size of the graph too, right? For like how many vertices there are.
Well, that's what I'm saying. Yeah, I give you the number of vertices. Then I say the probability that an edge will be between arbitrary pairs of vertices. Okay. Then you have a whole family of possibilities, right? Like, for example, the complete graph is possible randomly, but the chances of that are smaller comparative to probably having half of the edges in there and half of them not.
That's very interesting.
Right. So then you have this distribution of possible graphs. And then you say, among that distribution of graphs, what is the probability that the graph is connected? So that's how you could sort of create a probabilistic type question. I'm not an expert in that field, but that's how it works. And there's a whole ton of literature on it. It's pretty interesting because you're looking at these properties in general. You're saying, what's the likelihood of having this type of property in your graph?
Dan, who you
I didn't learn that. I forgot to
Very
do
good
my
question.
laptop.
Is there any
Yeah.
possibility that you post, that maybe you send me,
Well, I
the
could
keys
send-
so that I can check
This one,
before
okay,
the
this is
exam?
just a challenge.
Oh,
You're not
this
gonna be given that one.
So basically,
This is just producing an example.
Yeah,
These are some small examples.
okay, so here
Yeah,
I'm kind of confused a little bit because you said those cases were not
yeah,
allowed.
that one is allowed.
area of those
But
Yeah, I
what
have the
if they
picture
go
here.
through the
Actually, I think I
case?
have that one here. Hang on a second.
I want to say, input your shape, if it's a square, then
you're
there's an
trying to
equation,
check.
there's an equation for the area, if it's a square. And then if the hexagon.
Number 4, right?
Right.
So if I'm doing if else,
You need more than basement though.
I need more than that, okay?
Yeah, I mean, like, if, else if, and then else,
Okay.
or just two else.
Okay,
Here.
I'll send you it.
Okay.
Maybe you can figure it out, I don't know how to do it. Because it's, I could write 3 different programs to do it, it's really easy, but I'm trying to do it all in one. So I can-
Did I allow loops? I can't remember now.
No, you did not allow loops. That's
Okay,
all
yeah, so
I'm
order
confused.
1, it would only be that one then, right? Oh, yeah, yeah, so I allowed these, right? Multi-edges, but they have to have
Yeah.
different
Different
arrows.
orientation.
So
Yeah.
else if. check
So it
is
looked like that.
if, but
I think there's
Order
16,
So
right?
You don't do separate checks.
Or more than 16,
It's
actually.
more like one check. Like
I mean,
something's
order
good,
one,
good to
I'm
go.
just, I mean, order
And that's
3 I
it.
can
You
figure
have
out.
one statement.
Mhm.
But
And you have three
I was
different
just
sections,
wondering,
only
because
one
in class you said those were not
So I write
allowed.
that. I write
Yeah,
that.
Like,
so
if
it would
this
just
is
be
not
this, it would
allowed.
just be an isolated vertex then. That's the only one.
Okay.
Okay, but in order to be a diagram, don't you need an orientation?
No, it doesn't,
Not
you
necessarily
don't have to
can
have
be-
edges. Yeah, you could have, so order 2 would be this, right? You'd have
So how do you?
2 vertices,
place the triangle?
one edge, and then a
Okay.
digraph
So
going.
also you said we're not allowed to use, I mean, we can have, for example,
Like
something
the
like
number.
this with the same
Yeah,
orientation,
they have to have opposite, like that.
opposite.
Okay,
And then you can get the area.
Oh, right.
Yeah.
So,
right, but you have to be able to
Sounds good.
specify that it's.
so it makes sense. So here, for example, this,
It's like if you, I'm gonna say like.
so obviously this one,
I think like strength, it's like if I take.
And then if I have a
what
directed
if
arrow,
I do?
you see that this will be isomorphic to if it went the other way. So draw an edge between them and now orient it somewhere. And then you see that would be isomorphic to if it went the other way.
So, obviously, this would be, I mean, it's the same thing as this. same.
Yeah, it is. It's isomorphic, yeah.
Okay, what if I draw 2 of those but with 2 loops?
Well, loops aren't allowed.
Okay, you're
Yeah.
not allowed it.
Yeah.
No,
I was like,
As soon as you allow
does he want
loops, as soon as you allow, the problem with the loops is that you create an infinite number, right? Yeah,
So I was
that's the
like,
problem.
does he want loops
Like
or
just-
not? Okay,
This is the only thing that's allowed with multi-edges. So it's just like graphs before, it's just you could have going there and coming back.
sounds
You
good.
can get that.
You
This
have-
is more,
I mean, this one was a complete guy that was like 2, 2, 2 every.
yeah. Well, this one might not be, maybe it's, is it 2 for
I
everything?
thought 2 every.
Oh, really? Oh, okay. Yeah, that was the Peterson graph, so that's
Yeah.
interesting.
Okay, so I'm kind of confused about the notion of tournaments.
Don't worry about them. They're not really that important. It's just take a complete graph and then orient it, and that's a tournament. Some tournaments are not going to be that useful for applications. Other ones are useful. The useful
So,
ones
it's-
are
so
the
the
ones.
orientation is just random.
Yeah, it's random.
Just very random. So
Yeah.
you want anything
Yeah.
random.
So that problem is a challenge problem because it's actually very difficult. If I give you a complete graph of 5 digraph on 5 vertices, and you create this tournament, it is very difficult to tell if one tournament is isomorphic to another one, right? Yeah. So it's more of a challenge. Yeah, it's more of a challenge problem. I just mainly wanted you to think about that because if you draw a few of them, you'll see in terms of it being a real tournament, like let's say you had 5 teams that had to play against each other. Some tournaments will be more fair than other ones. Like it would be unfair if one team had to play every other team, but one team had to play no one, right? That would make no sense. So like a fair tournament would be one where probably the equal number of outgoing is the same as ingoing and things like that.
So this one is not due, right? Just for practice.
It's just for practice.
Okay, so
Yeah.
what is a self-centered graph?
Oh, it's defined right here. It says a graph is self-centered if all the vertices lie in the center of the graph.
So
Yeah,
like,
I'm just making that up. That's not like something you have to memorize.
yeah.
It's not like a math problem.
So let's say something like
It
the.
doesn't have to be a digraph. It could
Anything.
be just a graph. Yeah.
Okay,
like that.
so
So see, if you're KN, you're definitely, everything is in the center, right? For example, if I just draw this,
So
everything is distance 1, right? So the center is the same as this, right? Is there something like this that's not KN? That's what
So
that
I
question
didn't
is.
get that, is I just-
Can you think of a graph where everything,
Java is taking syntax.
it's not gonna be
That's like
distance
any
one, you
question
probably have to
in,
go more than
like,
distance
in
one,
specific
because if it's
language,
distance one, then it's
generally
definitely a
like
complete graph, right?
syntax,
But
unless
if you,
it's
could
like
you think of something where everything has the
problem.
same, it's probably gonna be
So
highly
syntax stuff
symmetric,
is what you want.
okay?
All right, thanks.
Well,
Yeah,
what about that
um,
first one that you did, that Peterson graph?
Yeah.
How far apart is everything?
Hey,
Well, but from this one to this one, is it 3 or no? Oh, no, it's a 2.
Yeah.
So if everything is 2, wouldn't that be a self-centered graph?
Yeah.
Because the center would be the whole thing, right?
Yeah.
Yeah. So that's what I'm kind of looking for.
Oh, you just. that is-
I defined it. I made that up. That
Gotcha.
definition. It's just kind of a funny definition.
So, thank you.
Yeah.
I mean, the thing I'm mostly concerned about is just probing stuff.